Have you ever wondered how a simple box become one of the most important test problems for engineers? The lid-driven cavity, the hello world or CFD. In today's episode on Aeromathix, we will validate one of the benchmark results published by Gaia. I will show you how to build it, good mesh quality, and extract real results. Let's start our journey. From Ansys Workbench, choose Fluent from the toolbox on the left and drag it. Right-click on Geometry and choose Design Modeler. Let's start with XY plane. As you can see, there is a scale for 40 meter. I will zoom in to make it easy to recognize the domain dimensions of 1 meter. Insert a new sketch for XY plane. Choose Rectangle. Start from the origin and drag it. Now we need to add dimensions for 1 meter. As a gaze research, we can choose the insert dimensions by semi-automatic or general. They both will make the same thing. For semi-automatic, it automatically identifies all dimensions you have. Set to 1 meter and again for horizontal line. Now we need to convert the sketch to surface. From concept, choose surface from sketch, apply it for sketches that we have, and press generate. This all things that we want from design modeler. Now we will move for mesh. So let's close the modeler and open the mesh. Here's our geometry in mesh. We need to make a uniformly structured mesh as a reference. They had worked on different Reynolds number values and different settings for mesh. I will work on 129 grid and Reynolds number value of 100. From mesh sizing, we want to choose all edges. Press on Z. Ensure that the selection is edges from the above, this one. Press on Ctrl to select all edges, then apply to divide it into 129. I will change element sizing from type to number of divisions. Be 129. Change the behavior to be hard as it's simple problem, so we need it to be hard, not soft. As we see, the number of divisions increased from the first one. Again from mesh, choose face meshing and apply the whole domain. Leave the other setting as it. Now we can generate. It didn't take a lot of time as it's simple. It's structured and uniform as the results that we want to get. Let's see our statistics and its weakness. For its weakness, find the quality, mesh matrix, and choose weakness. In the study, it should be 0 or approximate to 0. As you see, it's very small, almost 0. The final step in mesh, before getting to setup, is to identify each edge. By edge selection, and select those 3 edges. Create name selection to P walls. Step 1 is moving, so we'll call that the moving wall. Let's check and see them. the three fixed edges and the moving one, as this. Before going to setup, we need to update our mesh. If you didn't make it, you won't be able to find it in the setup. Choose double precision. Solo processor is depends on the number of it in your PC. I will choose 8 and then press start. From general setup, pressure base is chosen as it's incompressible flow, steady no transit and no need for gravity. From model we see the default is K omega SST. We will change it to laminar. From material, we will ensure that the fluid is air with required density and viscosity. Let's move for boundary conditions. Wall will be stationary, so let's ensure about it. As we see, it's stationary. And the moving wall, as we have named it, it will be moving. So we need to add a speed. But first, we need to calculate a simple formula. Let's see how we can get it. From Reynolds number formula, we have air density, velocity, and this is what we're looking for. Characteristic length, in our case it will be 1, dynamic viscosity, and the Reynolds number will be 100. Let's copy the velocity and return to the setup. Choose moving rule and add the velocity value. We need to make some changes on residual. I prefer to not print it to the console to save memory. And change the conversions to 10 power negative 6 for all values. For lead-driven cavity, our aim is to recognize the change in velocity and vortex area. So, from Reynolds definition, choose New, Surface Report, Area Weighted Average. The scope it will be the interior surface body. Change the field variable to velocity instead of pressure. Make sure that you have choose print to console. From methods, be able to choose in one of them simple or coupled, or any one of the other types. As it's a very simple problem, I will choose simple. The final step before calculations is initialize. Both hybrid and started initialization works well for the problem. For this problem, we can add a huge number of iterations, like 3000. And now we can calculate it. It won't take much time, as it's a simple problem. I will stop recording and back again when it's become complete. Here we are again. As you can see, the residual looks very good, and also the average velocity. Now we want to present it in our domain. From graphics, contour, we need to work on velocity. At first, when you open it, you will see pressure. Then you can change it to velocity. As we need to present the results in all domain, I will leave it without choosing anything. And just, we need to press save. As we see, there is a high change at the top part of the domain, at the moving lead. At this part, you can see the change, which is the Let's enable field to see it as lines to make it more easy to see vortex area. You can change it to x velocity or y velocity, but actually we need the velocity magnitude only. From create, choose line. Horizontal will be x naught equals 0, y naught 0.5, x1 1, y1 0.5. Another one for vertical, y naught equals 0, x1 equal 0.5, y1 equal 1, and x naught it will be 0.5. Those lines are important to be able to see the change in velocity in x and y directions. Let's see it from general display. Choose our tool. As you see here is our horizontal line and vertical line. Now you want to see the velocity in x and y directions. From plots, choose xy plot. Be the velocity. Y-axis function, it will be velocity. Change velocity magnitude to x velocity. Horizontal. Okay, sorry, I will change x velocity to y velocity. We can save it for a report. Choose write to file, press on write and name your file and choose its location. I have saved it before. Vertical line. For x velocity, change x to be 0 and y to be 1 and choose the vertical line. You can make the same thing to save it as point for graph as we have made in y-axis. This is all we need from answers. I will just learn new extra thing for validation, how to compare it to the reference values. Open Excel. As we have saved y and x velocity, I put this will make it, and I will make the same thing for data from the reference. At reference, he had worked on the ratio between velocity and original. I will copy those two columns, the velocity ratio at 100 of Reynolds number and the y location. Let's get the ratio for our data from answers. To make it simple on Excel, as there are first two columns, I will just make on the first two cells and choose them and drag it to the final cell. If you choose any cell of this, you will see it follows the formula correctly without any mistake. Adding y and x velocity, I will just make the same thing for x and adding y. Here we are finally, here we are again. After adding all data and represent it on Excel graphs for u velocity and v velocity, the almost dots is for reference. The orange dot is for reference and the blue for our results. From these results, we can validate our setup, and actually that's all we want from this. Now you have seen how a simple square with a moving lead can teach us the fundamentals of CFD. If you learned something today, subscribe